Chapter 11, Universal Gravitation and Satellite Motion. This lecture will help you understand a short history of gravity. To understand the use and need for Newton's law of universal gravitation, we need to understand the universe. To Aristotle, the universe consisted of the heavens, the outermost realm of the cosmos, where the motions of the celestial objects take place, filled with ether, and the earth, the realm of our ordinary experience. The earth consisted of four primary elements: fire, air, water, and earth. These two realms were completely separate. Together they formed the cosmos, the world. His belief influenced thinking for 1,500 years. The universe as a noun simply means all the existing matter and space considered as a whole, the cosmos. In other words, the place to put all the stuff we see, interact with, and are. Cosmology is from the Greek kosmos, meaning world or order, and logia, study of. So cosmology is the study of the world or the study of order. The modern definition of cosmology is the study of the origins and eventual fate of the universe. The key questions of cosmology are: how did the universe begin? How does it change with time? Why does it look the way it does? What is the shape of the universe? How will it end? And what observations, evidence do we have to support our understanding? All the ancient people had some form of cosmology, if not by name. The Babylonians, Sumerians, Greeks, Mayans, Hindi, Chinese, and so on, all had some belief of how the universe began and how the people came to inhabit the universe. Aristarchus of Samos in the 3rd century BC proposed that the earth orbits the sun. Ptolemy in the 2nd century BC said that if the earth moved around the sun, the stars would seem to move forwards and backwards, a motion known as parallax and used by surveyors. Since no parallax was detected, he concluded the earth does not move. So what is parallax? Parallax is a displacement or difference in the apparent position of an object viewed along two different lines of sight, and is measured by the angle or semi-angle of inclination between these two lines. Parallax is used in surveying to measure distances. Parallax also gives us stereo vision. Astronomical parallax is the apparent shift in a star's position throughout the year. The background stars are stars very distant from Earth. No parallax can be seen. The closer stars seem to shift positions back and forth with respect to the background stars, just as your thumb at arm's length appears to change position with respect to the distance wall when you close one eye and open the other. It was the lack of observation of parallax that led the Greeks to think that the Earth does not go around the sun. The sun, moon, and stars all have simple movements in the sky, simple circular motion consistent with an Earth-centered system. The planets Mercury, Venus, Mars, Jupiter, and Saturn, on the other hand, moved with respect to the fixed stars, change in brightness, change their speed across the sky, and exhibit retrograde motion. The Ptolemaic system is a description of the cosmos where the Earth is at the orbital center of all celestial bodies. The universe consisted of a set of nested spheres, in which he used the epicycles to predict positions of objects. Ptolemy estimated the sun was at an average distance of 1,210 Earth radii. The actual distance is 23,250 Earth radii, while the radius of the sphere of the fixed stars was some 20,000 times the radius of the Earth. Ptolemy's model requires lots of epicycles, little circles, to accurately track planetary motions. especially the retrograde motion. The figure shows Earth at the center, then the Moon, Mercury, Venus, the Sun, Jupiter, and Saturn. The distant stars are on the celestial sphere. Tycho Brahe was a Danish nobleman known for his accurate and comprehensive astronomical and planetary observations. In his De Nova Stella, On the New Star, in 1573, he refuted the Aristotelian belief in an unchanging celestial universe. His precise measurements indicated that new stars, supernova, lacked the parallax expected and were therefore not atmospheric tailless comets as previously believed. And they were above the atmosphere and past the Moon. Using similar measurements, he showed that comets were also not atmospheric phenomena and must pass through the supposedly immutable celestial spheres. In the Copernican universe, there is no one center of all the celestial circles or spheres. The center of the Earth is not the center of the universe, but only of gravity and of the lunar sphere. All of the spheres revolve about the Sun, and therefore the Sun is the center of the universe. The ratio of the Earth's distance from the Sun to the height of the firmament, the outermost celestial sphere containing the stars, is so much smaller than the ratio of the Earth's radius to its distance from the Sun that the distance from the Earth to the Sun is imperceptible in comparison with the height of the firmament. Whatever motion appears in the firmament arises not from any motion of the firmament, but from the Earth's motion. The Earth, together with its adjacent elements, performs a complete rotation on its fixed poles in a daily motion, while the firmament and highest heaven abide unchanged. What appear to us as motions of the Sun arise not from its motion, but from the motion of Earth and our sphere, with which we revolve about the Sun like any other planet. The Earth has, then, more than one motion. The apparent retrograde and direct motion of the planets arises not from their motion, but from the Earth's. The motion of the Earth alone, therefore, suffices to explain so many apparent inequalities in the heaven. Hans Lippershey was a German-Dutch spectacle maker and is commonly credited with invention of the telescope. Galileo Galilei was an Italian physicist, mathematician, engineer, astronomer, and philosopher who played a major role in the scientific revolution. He has been called the father of modern science. Galileo championed heliocentrism. The Sun is at the center of the solar system. Galileo invented the astronomical telescope by improving on Lippershey's design. And he was convicted of heresy in 1616 for his teachings and his beliefs. At the time of Galileo, the common belief was the Earth was the center of the solar system. Following Aristotle, the Earth was seen as imperfect, while the heavens were perfect, perfect spheres moving in perfect circles. With the telescope, Galileo was able to show that the Moon had mountains and valleys. It was far from the perfect sphere envisioned by Aristotle. Sunspots are cool regions in the photosphere of the Sun that appear dark because the surrounding regions are so much brighter. In observing the Sun, Galileo saw a series of imperfections. He had discovered the sunspots. Monitoring these spots on the Sun demonstrated that the Sun, in fact, rotated. Furthermore, later observations by Francisco Sizzi in 1612 suggested that the spots on the sun actually changed over time. These observations show that the sun, like the moon, was not the perfect sphere of Aristotle. When Galileo turned his telescope to observe Jupiter, he saw what he initially thought to be previously unobserved fixed stars. After continuing observations, it became clear that they were not fixed, and in a matter of days he had come to the conclusion that the new stars were in fact orbiting Jupiter. He had discovered the largest moons of Jupiter. These are now known as the Galilean satellites of Jupiter. They are named Io, Europa, Ganymede, and Callisto. The implications of the discovery of objects orbiting a planet were part of what pushed Galileo to argue for a sun-centered cosmos. Jupiter's moons countered a key argument against the Earth orbiting the sun. Critics of Copernicus' sun-centered cosmos said that if the Earth moved, the moon would be unable to orbit the Earth. The Galilean satellite showed that the moons could orbit another body. The answer of why had to wait for over 100 years. Further observations by Galileo show that the planet Venus underwent phases like the moon. This could only happen if Venus orbited the sun and not the Earth. The top image is a modern image of Saturn. The bottom is a drawing made by Galileo. Galileo discovered the rings of Saturn, which he initially mistook as a triple planet due to the poor resolution of his telescope. Galileo again showed that the Aristotelian view of perfect heavens had serious flaws. The Aristotelian view was that the Earth could not be moving because if it moved, objects in the air would be left behind. Galileo's experiments on inertia showed that the objects in air would stay with a moving Earth. A body moving on a smooth and frictionless horizontal plane would neither accelerate nor decelerate, but will continue to move at a constant speed. Such a body will only stop when another force stops it. From 1570 to 1600, Tycho Brahe compiled observations of stars and planets and noted how the planets Mercury, Venus, Mars, Jupiter, and Saturn moved through the sky. He made the most precise observations that had yet been made by devising the best instruments available before the invention of the telescope. The image shows the positions of Mars in the sky as determined by Brahe compared to the modern method of determination of Mars's orbit. Johannes Kepler was a German mathematician, astronomer, and astrologer who worked for Tycho Brahe from 1600 to 1612. Kepler attempted to calculate the orbit of Mars using the model of Ptolemy. The model of Ptolemy failed to reproduce the orbit. In early 1605, Kepler was able to create his own model that generally agreed with Tycho's observations to within 2 arc minutes, which was the average measurement error at the time. By using an ellipse to model the orbit of Mars, Kepler developed 3 laws of planetary motion that are now known as Kepler's laws and published in his Astronomical Novae in 1609. Kepler's first law of planetary motion is that planetary orbits are ellipses with the sun at one focus. A circular orbit is a special case of an elliptical orbit. Kepler's second law of planetary motion is that an imaginary line connecting the sun and planets sweeps out equal areas in equal times. In practical terms, this means that a planet would move faster when closer to the sun and more slowly when farther away. Kepler's third law of planetary motion is that the square of a period of planet's orbital motion is proportional to the cube of the semi-major axis, which is the average distance. Kepler's third law compares the motion of objects of orbits of different sizes. A planet farther from the sun not only has a longer path than a closer planet, but it also travels slower, since the sun's gravitational pull on it is weaker. Therefore, the larger a planet's orbit, the longer the planet takes to complete it. Using the orbit of Mars, Kepler was able to show that the sun, not the Earth, was at the center of Mars's orbit, and that the orbit of Mars and the orbit of Earth are elliptical. Kepler was also able to show that the orbit of Mars and the orbit of Earth were tilted with respect to each other.